Okay, so in this toddler on a playground swing question, what they're asking you to think about is the tangential acceleration. And they're asking you to, different people have different versions of this question, asking it for different points on the swing. Is there a tangential acceleration and which direction does it go? So let's just clarify again what tangential acceleration means. So if we're thinking about something moving, so if this is the middle point and things are moving to either side of this, like a pendulum, then if the acceleration is totally towards the center, so if it's like this, if that's the acceleration, then there's zero tangential acceleration because it's totally towards the center. But if there's some piece of the acceleration that's this way, then there is a tangential acceleration. Okay, so this part right here is the tangential part. Okay, and so for this problem, what they're asking you to do is consider different points on the swing and the direction she's moving and thinking about whether or not there's tangential acceleration there. Okay, so let's make this a little bit smaller over here. Okay, so let's think about, I didn't pick a particular version of this, but instead I wanted to think about the toddler on any given point. Okay, so if we think of this center point that she's going around, so this is when she's hanging straight up and down, and then she's going to move like a pendulum, right, up to her maximum point. This will be her maximum height when all the energy has been converted into potential energy. And same thing here. This will be her maximum height on this side. And from here, she'll always go down, and from here, she'll always go down. Here, though, she could be going this way to the right or this way to the left. Okay. We might also be considering some points in between that. And the question is, how do we think about whether or not she has any tangential acceleration? Okay, so if I draw a free body diagram for the girl in any one of these points, her free body diagram is always going to have gravity pointing down, and then it's going to have the force of the rope pointing some direction, right? So if she's right in the middle, the force tension of the rope is going to be straight up, but if she's to the right of that middle point, then force gravity is going to be pointing down, but then the force tension is going to be pointing at some angle. Similarly, on the left-hand side, it's going to be pointing some piece like this, right? So then the question is, if we think about acceleration, how do we decide from these two pieces of information whether there's some piece of the acceleration that is tangential to her path? So is there some piece that's along the direction of her path? Well, if we just look at these free body diagrams, right, they tell us this automatically. If there is some piece of the force that is not towards the center of her path, then there must be some tangential acceleration. So we see that in this case, the center one, there's no force not toward center. Toward center, right? But in both of these cases, if we break this down, so this will always be towards our center. Okay, so if I break these into their components, the force tension is always going to be towards the center of her path, right? Because the rope is pointing back towards the center. But the force gravity here, it's going to have some component that's opposite to the force tension, but it's also going to have some component this way, right? So this one has a tangential acceleration. Similarly here, this piece, there's going to be some piece of tangential acceleration. So the direction, so in both of these cases, yes, there is some tangential acceleration, right? And the direction of that will be the direction of this, of the force not towards center. right? And this is coming from the idea that F net is equal to mass times acceleration, right? So if I have I'm breaking my F net into two directions, one tangential and one towards the center, then that'll tell me about the acceleration towards the center or tangential. So this is one of those key ideas that I wanted you to take about out of the pendulum kind of problems. Okay, and this Belliard problem represents a lot of what people were struggling with for momentum, and particularly momentum in two directions. So I figured working it out would just help people think through this. So what we have is a billiard ball that's coming in along this path, and then it's bouncing off the wall and going off along this path. And the question that we're trying to think about are like the direction of the change in the momentum and the magnitude of the change in momentum, right? And we know that there must be a change in the momentum here because this railing is outside the system. So we have the billiard ball momentum is not conserved because it hit the railing. Okay, so in thinking about this problem then, what we have is we have some incoming momentum vector that looks like this, right? And we have some outgoing momentum vector that looks like this. And the question is, what's the change in the momentum as a result of this? So the easiest way to think about this is by breaking it down into x and y components. So our initial incoming momentum has a y and has an x that looks something like this. So this is p I y, and this is p I x. And similarly, the final momentum has something like that. So this is p f x, and it's p f y, right? And in all cases, we know that momentum as a vector is defined to be the mass times the velocity vector. So we know these vectors are being defined by the direction of the velocity, right? Because that's the vector in these momentum problems. Okay, so then the thing that we need to do is we need to say, how does the momentum change in the x, and how does it change in the y? Right? So let's start with the x. So in the x direction, we have an incoming I probably need some angles in here. So my initial angle, this is measured from the vertical, is 50, so that means measured from the horizontal, it's going to be 180 minus 50 is 130. So my picture isn't very good there. Or sorry, it should be 90 minus 50. So that's not 130, but rather 90 minus 50 is 40. Okay, and then the outgoing measured from the vertical is 43. So again, measured to the horizontal like I've drawn it, 90 minus 43, 45 would be 45, so it's 47. Okay, so what do I have in the beginning for my x direction? So let's start with x direction. In the beginning, I know that the change in the momentum in the x direction is defined to be the final in the x minus the initial in the x, right? So in the final in the x, I have whatever my mass stayed constant, and so I have a final velocity, and it's times the cosine of that angle too, so 43 degrees, or 47 degrees is what it is. And in the initial, I had that same mass, but now I had a different initial velocity, and again, I'm using cosine of 40 degrees. Okay, so here I find that by plugging in some values that I have originally, or my final in the x direction was 0.22 kilogram meters per second, and in my initial it was 0.33 kilogram meters per second. And so the difference between those should tell me it's a negative number actually. So I get negative 0.113 kilogram meters per second in the x direction. So what this actually tells me is that in the change in the momentum in the x direction, instead of being like they've depicted it in that diagram, is actually going this way, right? So the initial velocity was this way, and but the final velocity was bigger in the opposite direction. And so that leaves me a change in the momentum that's to the opposite. So this is actually the change in the x. Okay. So now we do the y direction. Okay, we do the same kind of thing. Change in py is equal to the fy minus the initial y. Now we have sines instead of cosines that we're dealing with because it's the y. It's the opposite of my angles that I have. Minus mvi sine of 40, right? And so then plugging in some numbers, I find that my final in the y is 0.2413 kilogram meters per second, and my initial in the y was 0.279 kilogram meters per second. And so the difference between those, again, it should be negative 0.0383 kilogram meters per second. So what this actually tells me is also that I was going down. My change in my momentum should be down instead of up. So what I draw then next is to find the total change in momentum vector, right? I take these two together and I add them. So I have my change in momentum in the y, and I add my change in the momentum in the x, and what I get is my total change in the momentum, right? And so I'm just taking literally these numbers here and here, and I'm going to put those in together. I'm going to use Pythagorean theorem, and I'm going to get that delta p. So I'm just going to use a squared plus b squared equals c squared. And I can do that because I've set this up to be x and y, which I know are perpendicular to each other. So taking those numbers, what I find is that my value for c here, or my change in momentum value, is 0.1194 kilogram meter per second. Okay, so that's my value for the change in the momentum. To get the angle, this is the angle I would probably focus my attention on. And so what I'll use there is tangent. So the tangent of that angle is equal to opposite. So this is my y over my adjacent x. So I just use those same numbers again. And I find that my angle should be 18 degrees from this point. And so we noted that in LonCampa, what it was actually looking for is for me to go from the horizontal around, right? So if I think about where that's going to take me here, I think actually the way that I've set it up, right, this should be the correct angle that it's looking for, given my, no, it should be below the horizontal. So I'll take 180 plus 18. So 180 plus 18 should be my 198 degrees, because this is actually below the horizontal, right? So if I go all the way around, that's the angle that it's looking for. Except for that's not right. That's not the angle it's looking for. It would be 180 plus this angle. So this angle. So that angle is, this is 90 minus 18 is 72. And then this is, again, 90 minus 72 is 18. Oh, so it was right. 18 plus 180. So 198 degrees is the angle from the original x-axis. Okay, so that's the billiards problem.